I'm Tony Debling, and we're going to spend 30 minutes looking at the key points to understand for your A2 statistics examination. I'm going to start with correlation. Here's a typical question. An ornithologist believes there's a relationship between tail length and wing length of female hook-billed kites and takes a sample of 10 of them, measures their tail lengths and wing lengths and stores the results in the table. Now she plans to use a linear regression model based on the data and is looking to estimate the wing length of other female hook-billed kites on their tail length. So a first point to notice is that when you're using a regression line, you should only use it to predict a response variable from the explanatory variable. This is because the recipe for calculating the regression line gives you a different line if the variables are reversed. So in this instance, as we're estimating from the tail length, t is going to be the explanatory variable. This means t is going to go across the x-axis. So here I've plotted the various data points and I've drawn in an estimate. Okay, prediction inside the range of the data is called interpolation. Prediction outside the range of data is called extrapolation. It's inherently risky as there's no evidence that the trend will continue either side of the range of data. So the ornithologist attempts to calculate the product moment correlation coefficient, gets a value of 1.3. And a common question is, how can she identify this is incorrect without carrying out any further calculations? And the answer is clear. You should know that the correlation coefficient should always be between -1 and +1, -1 being perfectly negatively correlated, +1 being perfectly positively correlated, and 0 meaning no correlation at all. You may be asked to calculate the product moment correlation coefficient for a table of data, and we're going to do that with the ClassWiz calculator. And here we will choose menu and option 6, statistics functions. We get a second menu. We're going to choose option 2, y equals a plus bx, because we want to do a linear correlation. At that point we get the opportunity to enter the table into the calculator. Notice that the x is the explanatory variable, so the t values go into the x column. Y is the response variable, so the w values will go into the y column. When they're all completed, choose option 4, and the calculator calculates the equation of the regression line, y equals a plus bx, and it calculates the product moment correlation coefficient, which is r equal to, in this case, 0.7628. Sometimes you have to explain the value of the gradient in context. What does it mean? And the gradient will mean that an increase of 1 millimeter in the tail length, or an increase in 1 in the explanatory variable, gives rise to an average increase of 0.6875 in the wingspan, the response variable. The last part of the question asks you to do a hypothesis test at the 1% significance level, looking for evidence of correlation. Hypothesis tests for correlation will always have a null hypothesis saying that the variables are uncorrelated, so that r or rho equals 0. In this case, we want to see if there's evidence that there's positive correlation, so our alternate hypothesis will be rho greater than 0. So this will be a one-tailed test. To calculate the critical value for row, we need to know the sample size, which in this case is 10, and the significance level. We return to our formula booklet and look at the critical values for correlation coefficients. Our sample size is 10 and our significance level is 0.01. So the critical value will be 0.7155. So here our correlation coefficient of 0.7628 will be inside the critical region, which will be between 0.7155 and +1. So that means there's sufficient evidence to reject the null hypothesis. So we reject the hypothesis that there's no correlation, and we accept at the 1% significance level that there is positive correlation. So in the context of the female hook-billed kites, we can say there is statistical evidence at the 1% level of significance that on average, female hook-billed kites with longer tails will have longer wings. Regression lines can also be used to approximate exponential relationships. Let's take a look at this example of a table of data showing the density of bacteria in n,000 per centimetre cubed over a period of time t in hours. This isn't a linear relationship. However, if we code the data, changing the variables x to match t and y now to match the log base 10 of n, we can find we get a very tight linear relationship. In fact, the correlation coefficient here is 0.999, and the equation of the regression line has been given to be y equals 0.7606 plus 0.0635x. We're told that the data can be modelled by an equation of the form n equals a times b to the power of t. For these, we always take the log of both sides. So we get log to the base 10 of n equals log to the base 10 of a, b to the power of t. We expand the log on the right hand side to give log a plus t times log to the base 10 of b. And then that matches y equals log to the base 10 of a plus x times log to the base 10 of b. So we compare coefficients of this equation with the regression line. We compare coefficients of this equation with the regression line, and we see that log to the base 10 of a is 0.7606. So a equals 10 to that power equals 5.762. Similarly, log to the base 10 of b equals 0.0635. b is 10 to the 0.0635 equals 1.157. Okay. We're asked to give an interpretation of a. Well, if you put t equal to 0, then n would equal a. So a is the initial value of n. So that's the initial density when we start measuring. Then with b, if you were asked for an interpretation of b, then b is the population multiplier each hour. If the power of t increases by 1, then b to the t plus 1 is b times b to the t. So we can see that n would be multiplied by b. And finally, we're asked to explain why it's not reliable for estimating the bacteria after 24 hours. And again, this is outside of the range of data that we've used, so it's not reliable as extrapolation. Let's move on to some probability. A machine is selected at random from the sample machines and test positive for the fault. And we have to calculate the probability that the machine actually has the fault. So let's complete our tree diagram first. 0.2% of the machines have the fault. And of those that have the fault, 0.70 test positive, and 10% of the machines without the fault test positive. So we can complete the tree diagram, and we can see that the probability of being faulty and testing positive is 0.014. The probability of not being faulty and testing positive is 0.098. So we're looking to calculate the probability that a machine is faulty given that it tests positive. I look at the Venn diagram. We can see here the probability that it tests faulty given that it's tested positive is going to be 0.014, and we're going to divide that by the probability that it tests positive, which is going to be the sum of these two values. So that gives us a probability of 1 out of 8. So how useful is the test? Well, it's not looking terribly useful, given that most test positive results do not have faults. So if test positive, there's only a 1 in 8 chance of the machine having the fault. Let's move on to the next part of the question. Servicing the machine, 2 components are checked for wear and tear. We've got event A, component alpha needs replacing, event B, component beta needs replacing. We know probability of A is 0.35, probability of B is 0.55, the probability of neither is 0.28. Okay, to work out the probability of the overlap of A and B, we use the probability of AUB equals probability of A minus the probability of A intersect B. So 1 minus 0.28 equals 0.35 plus 0.55 minus the probability of A and B, which means the probability of A and B is 0.18. So then we can calculate the remaining values to go into A and B. Now we're in a good position to answer any questions. It says show that A and B are not independent. So if they were, the probability of A and B would have to equal the probability of A times the probability of B. And as 0.18 doesn't equal 0.35 times 0.55, the events A and B are not statistically independent. The probability that component A or component B needs to be replaced but not both is simply the sum of 0.17 and 0.37, so that's 0.54. And finally, remember that mutually exclusive events are when they don't overlap, so the probability of A and B is 0. Let's look at a problem that requires the standard normal distribution. We're told that the call times at a call centre are normally distributed. We know that the mean is 16, but we don't know the standard deviation. We're also told that 10% of the calls take longer than 22 minutes. This type of problem is solved by comparison with the standard normal distribution. So the standard normal distribution has mean 0 and standard deviation 1. We can relate these two distributions. The x distribution will be sigma times the z distribution. Multiplying by sigma spreads out the values of the z's so that they have a standard deviation of sigma. And then we add 16 to shift the mean from 0 to 16. Next, we add in the other information, and that is that 10% of the calls take longer than 22 minutes. So the area of the tail of each distribution is going to be 0.1, and for the area in the run-up to the tail will be 0.9. So for the standard distribution, we can calculate the corresponding Z value. We use the class Wiz calculator. We choose the menu option 7. We choose the inverse normal distribution. This goes from the area to a value. We choose option 3 then. We type in the area 0.9, the standard deviation 1, and the mean 0. So this tells us that the value, the Z value that gives 10% on the right hand tail will be 1.2816. So now we have two values, a value of the X and a value of the Z, which we can plug into our equation. And so we get 22 equals 1.2816 times sigma plus 16. We solve this for sigma and we get the value 4.6818. So this is what we had to show. Next we have to calculate the percentage of calls that take less than 13 minutes. So here, now we know the mean and the standard deviation of the X distribution. We can simply use the class Wiz. We choose menu option 7. Here we're going to choose the normal CD, which is option 2. We enter a lower value of 0. We enter an upper value of 13. This is to calculate this area here. We know the standard deviation is 4.6818. We know mu is 16. We enter those. We get a probability of 0.26. So the probability that X is less than 13 is going to be 0.2605, and therefore it's a probability of 26.1%. Okay, the next part of the question. The supervisor in the call centre claims the mean is less than 16 minutes and he collects his own data. So for him, the distribution of calls, we don't know the mean or the standard deviation, but we do know that 20% of the calls take 17 minutes or more to complete, and 10% of the calls take 8 minutes or less to complete. So we can use our calculator to calculate the corresponding Z values for the right hand side and the left hand side of these distributions. So here we're going to do inverse normal, choose option 3. Here the area 0.1, we're now looking for this Z value here, and we get the Z value as minus 1.2816. And now we're going to look on this side here. The area in the run-up to this tail is 0.8. So we're going to go through exactly the same cycle. Now we put the area in as a 0.8. When equals, we see the Z value is going to be 0.8416. The X value 8 corresponds with a Z value of minus 1.28. So we can get one equation. The X value 17 corresponds to the Z value 0.8416. So we get another equation. We solve them simultaneously. We get sigma equals 4.238, mu equals 13.432. So in this instance, the mu is supporting the supervisor's view that the mean is less than 16 minutes. Let's look at another variant. Here we have the same distribution, x twiddles n 16, 4.68 squared, so it's a normally distributed variable, mean 16 and standard deviation 4.68. But now the evidence that the supervisor has is based on a sample of 16 calls, and that sample of calls, he calculates the mean of that sample of calls to be 14.2, and we want to know whether that supports her view that the mean is less than 16 minutes at the 5% significance level. This is a bit more sophisticated. So here we have a hypothesis test. At H0, the null hypothesis is that mu equals 16. H1 is that mu is less than 16. So this is a one-tailed test. We're going to be interested in the distribution of means of samples of 16 calls. That's the X bar. They will be normally distributed, still with a mean of 16. However, the standard deviation will be the standard deviation of the population divided by the square root of the number of samples, in this case 16. So in this instance, the standard deviation of the means would be 1.15. That's based on taking a sample of 16 from a normally distributed population with mean 16 and standard deviation 4.68. So here we want to calculate the probability that the mean of a sample of 16 calls would turn out to be less than or equal to 14.2. We use the classworks calculator. We choose menu option 7, and here we're going to choose normal CD. That's option 2. We put in a lower value of 0. We'll put in an upper value of 14.2. Here, remember, the sigma is the standard deviation of the means, so it's going to be a standard deviation of 1.15, 4.6 over the square root of 16, and the mean is 16. We do the calculation, and we calculate that probability is 0.0588. And because that is more likely, it's a higher probability than the significance level, we say there's insufficient evidence at the 5% significance level to reject H0. So there's not sufficient evidence at the 5% significance level to reject the proposition that the mean is less than 16. This problem relates to the binomial distribution. So first of all, let's refresh ourselves as to what the conditions are for using a binomial distribution. There are 4. There needs to be a fixed number of trials, 2 outcomes for each trial, success or failure, a fixed probability for success, and each trial needs to be independent of the other. So let's look at the problem. A company has requested a set of scratch cards for a competition and asked for a probability of 45% that each scratch card will be a winning card. And they're going to take a sample of 20 scratch cards from each of their 8 stores, and they want to calculate the probability that in at least 2 of the 8 stores, 12 or more of the scratch cards are winning cards. We have to do this in 2 steps. The first is, if we take a sample of 20 cards, we want to work out the probability that 12 or more are winning cards. So if we let W be the number of winners in a sample of 20, then W will be a binomial distribution. So it will be 20, the number of trials, and the probability of success in each case will be 0.45. So we want the probability that W is greater than or equal to 12. We have to convert this to 1 minus the probability that W is less than or equal to 11, because it's the less than or equal to calculation that the ClassWiz calculator will do for us. So we go to our calculator, we choose menu option 7, and here we're going to look at the binomial distribution, but we want to have the cumulative distribution, not the probability distribution. So you have to go onto the second page and choose option 1, binomial CD. We're going to choose a single variable. We're going to put x in to be 11, n for the number of trials as 20, p for the trials to be 0.45, hit the equals. It gives us a probability of 0.8692. We go back to the menu, put it into ordinary mode, work out 1 minus the answer, and we can see that the probability that W is greater than or equal to 12 is 0.1308. So now we can look at the stores. We're going to go through 8 stores, and we're going to take these samples of 20, and in each case the probability of getting 12 or more scratch cards is going to be 0.1308. So x being the number of stores with 12 or more winning cards, x will twiddle b 8 for the number of stores, 0.1308 for the probability of success. And we want to know that we want the probability that in at least 2 of the 8 stores this will be the case. So the probability that x is greater than or equal to 2 will be 1 minus the probability that x is less than or equal to 1. And we're going to go through exactly the same sequence as we did for the first calculation. We have to go onto the second page of the menu. We choose binomial CD. We're going to choose a single variable, but here x will be 1, n will be 8, p will be 0.1308. That gives us a calculation, the probability 0.718. We go back into standard mode, calculate 1 minus it, we get 0.282. So the probability that at least 2 of the 8 stores have 12 or more scratch cards which are winning will be 0.2820. The next part of the problem is to do with approximating a binomial distribution with a normal distribution. And we're asked to write down 2 conditions under which a normal distribution may be used as an approximation. And these 2 conditions are: the probability of success has to be close to 0.5. That is because we want to have a symmetric distribution. If it's far off 0.5, the binomial distribution is skewed. And we need a large number of trials. A random sample of 300 of the scratch cards is taken. We're going to assume 45% of the scratch cards are winning cards, and we're asked to use a normal approximation to find the probability that at most 122 of these 300 scratch cards are winning cards. So, if W is the number of winners in a sample of 300, then W would be a binomial distribution, 300 trials with a probability of 0.45. And we can calculate the mean of that distribution. It's going to be n times p, 300 times 0.45. This is in your formula booklet. So sigma squared equals np times 1 minus p equals 74.25. So the standard deviation will be 8.6168. So these will be the parameters we use for the normal approximation. So the normal approximation x to the number of winners would have a mean of 135 and a standard deviation of 8.6168. When we approximate a binomial distribution with a normal distribution, we have to use a continuity correction. So, to calculate the probability that W is less than or equal to 122, we actually calculate the probability that X is less than or equal to 122.5. So here we can return to our calculator. Now we choose a menu. We're now going to choose the normal distribution, normal CD, so that'll be option 2. We put in the lower value as 0, the upper value as 122.5, the standard deviation is 8.6168, the mean is 135, and we find the probability of this is 0.0734. So this is the probability that at most 122 of the 300 scratch cards are winning scratch cards, and this has been calculated using the normal approximation. The last part of the question says that given that 122 of the 300 scratch cards collected are winning scratch cards, comment on whether there is evidence at the 5% significance level that the proportion of the company's scratch cards that are winning cards is different from 45%. Here we would have had a null hypothesis that the probability of a winning card was 0.45, an alternate hypothesis that it was different from 0.45, which would mean we'd use a two-tailed test with a probability of 0.025 in each tail. So here our 122 is going to be outside of that tail because the probability of 0.0734 is greater than 0.025, and therefore in this instance there's not evidence at the 5% level to suggest that the proportion is any different from 45%. Our last slide is just a reminder to make the most of the formula booklet. We use these formulas in the probability questions. When you have independent events, the formula booklet documents the criteria for independent events. The probability of A intersect B is the probability of A times the probability of B. We use the critical values for the correlation coefficients. We also use the mean and variance of the binomial distribution when we approximated it with a normal distribution. And then also this formula here gives you a hint that the standard deviation of the means when we take a sample of n observations will be sigma divided by the square root of n, the number of observations. That's all, folks. I hope you found it useful. Good luck in your examination.